All right, look at another example. Offspring of certain fruit flies may have yellow or ebony bodies and normal wings or short wings. Genetic theory predicts that these traits will appear in the ratio 9, 3, 3 to 1. Yellow and normal, yellow and short, ebony and normal, and ebony and short. Researcher checks 100 such flies and finds the distribution of traits to be 59, 20, 11, and 10 respectively. What are the expected counts and the degrees of freedom? Okay, so let's first talk about counts. Do we have actual counts of things? And we're given the observed we have, but the expected we're given some sort of ratio. So we're going to have to convert the ratio into some sort of expected counts in order for this to work. And so what we can do is we can sort of think about if I have this ratio of 9, 3, 3, and 1, that means that 9 we can translate into 9/16 of the 100. All right, so let me kind of pause this and let's talk a little algebra sense here. Okay, so let's talk about that ratio of 9, 3, 3, and 1 for a second. If I have 100 fruit flies and I expect 9, this ratio, one thing that I can do is I can just say, well, let me 9 times some amount plus 3 times some amount plus 3 times some amount plus some amount should add up to 100. Which will give me a way that I can break up all these different categories. So if I add this up, I get, let's see, 9 plus 3 plus 3 plus 1. So I should get 16x equals 100. Okay. So what does x equal? X would equal 100 divided by 16. Of course, we can reduce that. Let's see, so that would be, what, 50 over 8. Do one more, 25 over 4. Okay. And then it doesn't reduce any evenly after that. So let's talk about that 9, for example. The 9, if I multiply that by 25 that'll tell me how many of the 100 I expect to be of that yellow and normal. And if I take the 3 and multiply that by 25 same thing. And if I take the 1 times 25 seems kind of silly, that'll tell me the other amount. So that's where we're getting this these numbers from. Okay, so working out all those decimals that we just saw, we get those 4 numbers. And then our degrees of freedom would be 4 categories, because there's the 4 different types of fruit fly colors, I guess. And then -1 gives us 3 degrees of freedom. Okay, so the question then is this distinctly different than, are the categories different than what we observe, different than what we expect to see? So we're going to go back to our calculator and we're going to type in the observed numbers in list 1 and the expected numbers in list 2, and then we'll carry out the calculation from there. Okay, so if you'll turn your calculator on and go to your stat lists, let me get rid of this other problem that I had in there earlier, and we're going to type in our observed, so 59, 20, 11, and 10. That's what we observed. Okay, and then in list 2, we're going to type in those expected counts. Oops. Helps if I put a decimal in there. Okay, and then from here we'll carry out the test on the calculator, and then we'll do the formal write-up and just make sure that we're satisfying everything. Okay, so from here we're going to go to our hit stat and go over to test, and we want the chi-square goodness of fit. So you can arrow down, it's right there. And I have my observed in list 1, my expected in list 2, my degrees of freedom. Remember there's 4 categories, so minus the 1 gives us the 3. And we're going to calculate that, and it gives us that lovely number, so 5.67 with a p-value of 0.1287. Okay. So let's go back and finish up the formal write-up with the assumptions and the setting up the hypothesis stuff and stuff. Okay, so let's start with our assumptions. We have a random sample. We clearly have expected counts that are greater than 5. So we just want to list out all those expected counts. Our null statement is that the proportions of fruit flies are the same as the theoretical, and then our alternative is the statement at least one proportion of the fruit flies is not the same as the theoretical model. Alright, then we're going to set up our formula. Now keep in mind we already used the calculator to generate this number. We're just formally showing our work as far as how one would want to do this by hand. So the 59 minus the 56.25 squared divided by 56, the 20 and the 18.75, etc., etc. And we got a p-value of 0.129 with an alpha of 0.05. Okay, so p-value is bigger than alpha. What does that mean? That means we're going to fail to reject. There is not sufficient evidence to suggest what? Oh, well, it suggests that the distribution is not the same as the theoretical. So let me write that out there for you. And there you go. Alright, so that brings us to our next chi-square test. This is for a chi-square test of independence. And this is going to require a different calculator screen than we have ever had to deal with so far. We use this with categorical bivariate data from one sample. Okay, so let's kind of clarify the terminology here. Categorical means we're counting categories of some kind. Bivariate means there's two variables that we're measuring, and one sample means we're investigating one thing that just went out there and collected data once. The purpose of the independence test is to check that used to see if two category variables are dependent or independent, or associated or not associated. So you'll see those words used interchangeably. Associated versus not associated simply means associated means that one variable depends on the others, and not means independent. Great news, the assumptions are the same. So we got SRS in context, and we have that the expected counts of each category are greater than or equal to 5. Okay. Our hypothesis statement would sound something like this. The null is that the two variables are independent, and the alternative is that the two variables are dependent. We could swap out the word independent and dependent with associated and not associated, just be aware. And of course you want to add context to what we mean by variables and all these other terminologies. All right, let's take a look at an example. A beef distributor wishes to determine whether there is a relationship between geographic region and cut of meat preferred. If there is no relationship, we will say that the beef preference is independent of geographic region. Suppose that in a random sample of 500 customers, 300 are from the north, 200 from south. We also know that 150 prefer cut A, 275 prefer cut B, and 75 prefer cut C. Okay, so let me kind of go back and dissect this. If you manufacture meat, if you're in the cattle industry, you kind of want to know who your market is, who your customers are. And being here in Texas, we kind of understand that a good cut of beef is something to be proud of. So for us, it's really easy to imagine that region sort of determines the preference and quality of meat that one might want to enjoy. Other places don't quite barbecue as much as we do. Now, that said, that's being very biased as I describe this problem to us. That's what we're investigating is based on the numbers that we count, is there sort of a independence or dependence of region versus meat type? Okay. All right. So let's talk about some totals then. Based on the totals they gave us, if the beef preference is independent of geographic region, how would we expect to fill this table in? In other words, if I know that the north has 300, the south has 200, and then I have cut A, B, and C is 150, 275, and 75, how could one determine what we expect to see of something like this? Okay, and it kind of goes back to percents of things. Okay, so now notice that if I just look from north to south, that 3/5 prefer north. So what is 3/5 of 150? So if we just type in 3 times 150 divided by 5, we should get 90. And then south would be 2/5, prefer south. So 2/5 of 150, or 2 times 150 divided by 5, would be 60. Okay, and then I can go in this entire chart and I can do that same logic. So 3/5 of the 275 is 165, and 2/5 of the 275 is 110. 3/5 of the 75 is 45, and 3/5 of the 2/5 of the 75 is 30. Okay, so just want to say calm down on that. I'm going to show you another calculator skill related to this in a moment. But this would represent what one expects to see from the different categories. Okay, now kind of clarify how we did that. We took the row total times the column total and divided by the table total, or just basically what I talked you through about the 3/5 and the 2/5. All right, degrees of freedom. This is new for us. Normally it's n-1. In this case, or categories -1. This is not true for a independence test. We're going to take the row -1 times the column -1, and that's what's going to generate the degrees of freedom. Or in other words, if we just cover up a row and cover up a column and count the number left, then we can see, count the number of boxes, and that would also count as our degrees of freedom.